Good morning, everybody, and thank you so much for joining us today. And welcome to our speakers. So I appreciate you all joining EGU25. It's our General Assembly for this year, and it's also the biggest conference of geosciences in Europe and the second biggest in the world. So today we are kicking off our second press conference, and it's titled Hot Takes and Policy Quakes When Geoscience Meets Social Science. So while the climate crisis accelerates, finding integrated solutions, it's more urgent than ever. So today, our speakers will address key topics that will include the impact of global catastrophes, of food trade, public preferences for nature-based climate solutions, and updated IPCC emission scenarios that reveal the reality of failing to limit the warming to 1.5 degrees Celsius. So today we have Alice Wanner with us from the University of Natural Resources and Life Sciences in Vienna. We have Florian Ulrichien from the Alliance to Feed the Earth in Disasters in Lafayette, Colorado, USA. And last but not least, Chris Smith from the Vrije Universiteit Brussels, Department of Water and Climate, Brussels, Belgium. So thank you so much, and you can kick off.
Hey, thank you so much for having us today. I'm joined by my colleague, Maaike Jongnikkel, who's sitting among you. And I'm going to be telling you about some of the social science work we've been doing in our project Upsurge, where we're looking at how to use nature-based solutions to improve air quality, but also fight climate change. And I'll be talking about the differences according to some heat-related experiences across 6 European countries. So we're seeing a lot more nature-based solutions being picked up in European policies. This is also due to the fact that nature-based solutions, perhaps for those who don't know it, NBS, some might call them green areas or also green infrastructure. They're solutions to issues using nature, using plants is maybe sort of the easiest way to summarize it in one sentence. Now, NBS are used to fight climate change, but also to improve air quality, to reduce temperatures. They can also be used to improve the health and well-being of citizens. We all know green areas are good for our mental health as well. So NBS have a lot of great benefits that we can see and that are also being integrated into policies. But at the same time, when we're looking at cities, they're very compact areas. We have a lot of different interests, but also different uses coming together. So we face a lot of barriers when we try to implement NBS. This leads to us needing to make trade-offs. How efficient can an NBS be depending on how much space we have? How expensive will it be, honestly, to just implement it, but also to maintain it? Nature-based solutions need a lot of maintenance. And then we also have the idea of what do our residents in the neighborhoods want and expect from NBS as well. We also see that local conditions in cities influence what type of NBS are desired and needed. Each city has different issues they're facing, and so different NBS will come in question. How did we do this? So we were really interested in, like I said, what the citizens and the residents of cities think. Also, if they are willing to contribute, would a communal charge perhaps be acceptable? Or are they willing to maybe park their car further away, and that would cause maybe some extra time to get to their house or place of residence? To do this, we did a choice experiment, not to get too far into the methodology, but essentially it is a methodology we can integrate into a regular survey, and it looks something like this here. So the respondents are given multiple options to choose from. Each respondent is given a set or different sets at random, so nobody gets the same sets. They're all mixed up on what the levels are, as we would call them, within them. And the residents can choose between A, B, or neither. And it's also always important to give them that option to opt out entirely. So for today, I wanted to bring the topic of high temperatures and heat. So the questions we'll be looking at are residents even saying that they are affected by heat and high temperatures? And does the exposure to high temperatures influence their willingness to pay or to contribute in their time? Very simple question we posed. How are heat waves affecting your health and well-being? And we could see that roughly 60% or more in Greece, Hungary, Slovenia, and Poland really stated that heat waves were having a negative effect on their well-being. taking it one step further to negative effects on one's health. We could see that especially Hungary and Greece felt more affected than the other nations. We also saw that the Netherlands and the UK, sorry, typo, the United Kingdom, were feeling less impacted by heat on their health and well-being. The results of the choice experiment, we can, once we run our analysis, we plug them into a decision support tool that looks like the screenshot I'm showing you here. And what this does when we take option A and option B, we can adjust them, and then the bar charts will adjust accordingly and show us how many of the respondents would opt for A or B or opt out. And this is a really practical tool we use because it's interactive, so we can take it to stakeholders, we can take it to policymakers, to city governments, to play through different scenarios that they might want to implement. And also just ask them, where do you think thresholds are? How much do you think people are willing to contribute? How impactful do you think changing that accessibility to their home would be? And play through these scenarios. So the one today is, of course, temperature related, because that is the topic we are on. So I have in option A here, a very low temperature reduction, just 0.5 degree Celsius, but for that, your contributions would be low. So only a 5-minute shift to the accessibility of your home, only 10 euros per household per year as a communal charge for the upkeep, versus a much higher reduction, 6 degrees Celsius. But for that, you would have to take a greater disruption to your accessibility and also a slightly higher fee at 40 euros. And what we can see in the results here is that the Netherlands and the UK have quite high opt-out rates compared to the other countries, so they are not interested in these options. As to the same degree as the other countries, we can see very prominently Hungary is very interested in the -6 degrees. But we see otherwise that both of them are quite viable options. So when we have a decision support tool, we can also play through different scenarios of which one is more realistic to implement and what would achieve the solution that you're trying to find. Oh, I've lost my mouse. So kind of to summarize our main findings and also what we're doing with our insights into what the residents want, we collaborate with our project partners who are working on a lot of the climate mapping, identifying urban heat islands, for example. So we can kind of overlay the social science results with their mapping and figure out where are hotspots in cities to implement NBS. We have found that we have very different desires across the continent, of course, and that these can be linked to their exposure to climate change. Also air quality, but I'm not talking about that today. The temperature reduction through nature-based solutions is especially important to countries that are feeling higher temperatures, less important to those where it is not felt as strongly. I think that's pretty intuitive, but still that is a result, and it is good that we have it. The willingness to pay is linked to the exposure to climate change. So countries that are looking for a stronger temperature reduction are also willing to contribute in time or money for the solutions they want. But they do have to be effective. So we will contribute, but only if it really changes our neighborhood in the way that we desire and we want. Of course, when we start looking at deeper levels, when we start going into each of the national samples, we are seeing that aspects such as income, the built environment, the type of neighborhood they are in, if they have access to green areas, if these are high quality green areas, will also influence the decisions they make. Overall, we can say that it's very important for cities to not only communicate what is being constructed, but also what the idea behind it is. So what should be achieved through an NBS? Why was this the solution chosen for the area? And also the timeline. When we're working with plants, they do take time to grow. And sometimes neighborhoods can get a bit impatient about what they expect NBS to achieve in what time frame. So just clear communication between time frame and efficiency would benefit the development of our neighborhoods. Thank you.
Thank you so much, Alice. Now we're going to hand the floor over to Florian.
Thank you very much. I work for the Alliance to Defeat the Earth and Disasters, and we are a nonprofit who works at trying to make sure that even like if global catastrophic risks happen, we still have resilience in our food system. And the thing I want to talk about here today is food trade and how it relates to global catastrophic risks. And we're focusing here on food trade because it's obviously a very important part of the food system, because what you can see here is a map of all the food that is traded currently globally. And as you can see, like there's a lot going on. And also you like have few countries, like for example, the US or Brazil, that are exporting like to a lot of different countries at once. And so they're obviously like very important to the overall system. And the food trade is also like very relevant to the food system in total, because like 1/4 around of the food is traded. And this can be much higher for some countries, like for example, Singapore, which are much more reliant on food trade. And when we're talking about like catastrophes that can really disrupt food trade on such a scale, there aren't that many. Like I brought here a few as examples. You can have like cyber attacks that destroy electrical grid. Like we have geomagnetic storms, which can also disrupt the electricity we have. You can have things like a nuclear war, which obviously has a direct effects from the explosions. But you can also have longer term climate impacts if you have something like a nuclear winter. And similarly, you can have, for example, a large volcano that erupts and also cools the climate. And we generally group these for this analysis in like two large groups of catastrophes. We have like on one side, the large scale industrial disruptions. And here's the idea that your industrial capacity gets disrupted on such a level that you can't produce things like fertilizer anymore. And we have conducted studies in the past to figure out how this influences the yields, and we use this as the groundwork for this study. And also we have what we call abrupt sunlight reduction scenarios. And these are just scenarios where like aerosols are emitted into the atmosphere and they cool the climate globally. And also obviously, like if the climate is cooler, the sunlight is available, also plants just grow less well. And what we then wanted to figure out, like what would happen if these catastrophes happened, they reduced the yield that is available, and how would this cascade through our global food trade system? And we started with this by taking the trade data from the Food and Agriculture Organization for like the 4 main crops like wheat, soybeans, rice, and maize. And then built like a global network out of this, where we just has the network where the trade between the countries is the strength of the connection between the countries. And then we can take the yield reductions from the two groups of scenarios, like the sunlight reduction and the industry disruption, and apply it to that model. And when we're building that model, we also like corrected it for the re-exports of food between countries. And this means every country can just like export as much as it is producing. And so if you then have like a reduction in yields, you also have a reduction of trade, because like if you have less wheat available, then you can also treat less wheat. And our result gives like, our model gives like 2 main results. At the one side, we have like, it tells us what the change in trade community is. And a trade community in this context is just like a group of countries that are trading a lot with each other. And if I had been, for example, in a trade community with the United States, but the United States suddenly can't produce as much food anymore, then I have to find someplace else to get my food. And similarly, the model also lets us calculate like how this translates into changes in how much crop imports are available for the different countries. And I want to show you like 2 main results we have here. This is for wheat, and in the upper map you can see the effects of the large-scale industrial disruption, like for example by a geomagnetic storm. In the lower one, you can see the change after sunlight reduction, like a nuclear war, and the color just tells you like how much the trade community shifts in these scenarios. And a dark blue means your community stays the same as before, and a bright yellow means your community has changed completely. And as you can see, there's like quite a difference between those two figures. and you generally like have like a smaller disruption of the trade community in the large scale industrial disruption than in the sunlight reduction scenarios. And this is the case because in these industry disruption scenarios, usually like the countries that are producing a lot of food right now are also those countries that are using lots of fertilizers and pesticides. And so if you like generally remove access to these resources, then they all go down in a similar amount. Like if all your trading partners reduce by 10, 20, 30%, then you still have the same community. It's just less food available in total. And it's a bit different in the sunlight reduction scenarios because in this case, these temperature effects affect different countries differently. And they especially affect countries like the US and Russia who are producing and trading a lot of food. And so if they are disrupted, then this has consequences for many other countries because suddenly their main trading partner isn't available in the same way it was before. And the second thing I want to show you is how this then translates into import changes. So the scenarios we looked at had like a roughly 35% median yield decline. And what you can see here is how this translates to reduction in food imports. On the right side, you have like the finite reduction scenarios. On the left side, you have the industrial disruption. And the colors just mean like which crop we are looking at. And as you can see there, like the impact is much bigger for the sunlight reduction scenarios. And this is just like also the same explanation as in the slide before, that you just have the countries that are most producing most food are impacted most in these kinds of scenarios. And like to wrap things up here is, I think we've shown that food trade can be quite vulnerable to these major food production shocks. And we also have shown that generally, even if they are happening on the same magnitude of yield reduction, you can still see that these sunlight reducing catastrophes cause greater disruption to the food trade than the industrial disruption scenarios. And we think like one thing this also quite nicely highlights is that the global food system is just very concentrated on like very few countries, very few crops. And so if you have disruption in any of these, then you also quickly have like a very big problem that cascades to the food system. And this also builds to what we recommend with resilience. I think it would help if we have like a more geographic diversification, but also when it comes to crops, that we are using more different kinds of crops. We also suggest that it would be good to invest in the deployment of rapidly scalable resilient foods. And with this, we just mean like having kind of backup foods in the case you have like these disruptions. Okay, what could we do to feed people even in such events? And finally, it would be important to also even consider such major shocks in like things like trade agreement, national risk assessment. There are a few countries who do that, but most don't. And it would be great if we could do that more. That is all for my presentation, and I'm happy to answer questions later. Thanks.
Thank you so much, Florian. And now we're going to move on to our last speaker of this press conference, Chris Smith.
Good morning. Thank you very much. So this is work currently in progress, developed with my my colleagues in Oslo and a growing group of collaborators. So the basis for this is to show that the current set of IPCC emission scenarios are no longer limiting warming to 1.5 degrees. So the starting point for this is a group of scenarios produced by these socioeconomic models called integrated assessment models that submitted their emission scenarios to the IPCC 6th assessment report. There are over 3,000 scenarios submitted, and of these, 1,202 contained sufficient detail and were sufficiently close to both historical trends in emissions and energy system variables that they were useful for making climate projections. And this was done in the IPCC Working Group 3 report in 2022. There are three simple climate models that were used to analyze the climate outcomes. of these scenarios. And the reason why we use simple climate models is because we have over 1,000 climate scenarios. And then we also run each model probabilistically. So we run lots of ensemble members to sample the uncertainty in the climate response. So we're actually running maybe 1,000 scenarios, 1,000 ensemble members. We're running 1 million model runs. So we can't do this with full complexity climate models. We use these so-called reduced complexity or simple climate models that replicate the behavior of the more complex Earth system models. So in the Working Group 3 assessment report, there were 97 scenarios of these 1,200 that were consistent with the Paris Agreement definition of 1.5 degrees. So this was defined by the IPCC as either staying under 1.5 degrees entirely or exceeding 1.5 degrees with a small overshoot. There are actually rigorous definitions that I've put in the slide. And the 97 scenarios that were falling into this category had this label called C1 or category 1. And 9 of those 97 didn't overshoot 1.5 degrees at all. So these are the dark blue scenarios in the figure. You can notice that there are some wiggles in the projections, and this is the 11-year solar cycle that was included in the future climate projections. And I'll talk a bit more about the implications of that later when we do the climate assessment. One other thing to note as well is the model used to produce these scenarios was the model called MAGIC. This has a long history of being used in the IPCC for doing scenario projections, and it was the warmest of the 3 simple climate models. So this is a bit of a prudent assessment of the IPCC database. So what we're doing in this work is we are updating the historical emissions that are used to provide the starting point for these scenarios. In the IPCC, the last year of historical emissions is 2015, and we now update this to 2024 using the most recent emissions trends available from data sets such as the Global Carbon Project and other globally recognized emissions data sources. We are updating the climate baselines. So again, the IPCC assessed present-day warming to be the 20 years between 1995 and 2014, and they define this to be 0.85 degrees above pre-industrial. We have a project called Indicators of Global Climate Change that annually update these IPCC physical climate assessments, including the recent warming, CO2 concentration, and Earth's energy uptake. And we have updated these to more recent values. So we now use, as our starting point, we use 1.23 degrees for the last decade, and we have a last 20-year mean of 1.09 degrees for 2005 to 2024. And we also make some methodological updates as well. So one of these being that the solar variability in the future that I talk about, we don't include this in our updated projections. And the reason why is because when we assess consistency with targets such as the Paris Agreement, we want to define this in terms of the human contribution to climate change. So we want to isolate any natural effects from solar variability or sporadic volcanic eruptions. We still use solar and volcanic variability in our calibration of the simple climate model because we want to replicate the historical warming as best as we can. We also changed the model that we use. So instead of using MAGIC for this assessment, we use FAIR. And FAIR is a simpler model, but it's much more easy to calibrate to these present day constraints. And because we're running 1 million ensemble members and we're doing this in various different configurations, we can run this IPCC database of scenarios much more efficiently. So to show you what happens in terms of the emissions for these scenarios, the CO2 emissions and also the greenhouse gas emissions measured by CO2 equivalent, these 97 scenarios fall in this purple band. And between 2015 and 2024, we would need to have a reduction in emissions of between about 0 and 40% compared to 2050. So we should be well on the way to net zero already from a 2015 starting date in these 1.5 degree consistent scenarios. What we've observed in reality is a 4% increase in both CO2 and total greenhouse gas emissions. So we're now outside of the range of these 1.5 degree consistent scenarios, just looking in emission space. And what we're doing in this work as well, in order to run our climate projections, we take 2024 as the year of what's called harmonization. So we update the scenarios to start from 2024, and the emissions of CO2 and greenhouse gases look like this. So noting that we can't go from 2024 CO2 emissions to back to the purple line in 2025, this harmonization technique is what was done in the IPCC in order to construct these future pathways, and we've just updated this to a new historical emissions baseline. So what we see, if we compare what we were doing in the IPCC report with the updated climate model starting from 2024, then instead of 97, we now have 67 scenarios that are 1.5 degree consistent, but more of them are staying under 1.5 degrees. So we have 12 scenarios that don't overshoot with a 2014 starting date for both emissions and climate constraints. If we update this to 2024, then we lose all the scenarios that don't overshoot, and we're down to only 6 scenarios that are 1.5 degree consistent in terms of low overshoot. You can see here that the solar variability is included in these projections. So this is following the same approach that was done by the IPCC in the 6th assessment report. If we actually consider only the human component of warming, then starting from the 2014 baseline, you can see that there are actually fewer scenarios that are both 1.5 degrees without overshoot and 1.5 degrees low overshoot. And the reason for this is it's an artifact of how these model simulations were run. So in the comparison of the more complex models, we have to make some assumptions about how we transition from a historical period that includes volcanic eruptions to a future scenario period where we have no volcanic eruptions assumed. And there's actually an offset of about 0.2 watts per meter squared. So we have this artifactual cooling transitioning from the historical to the future in the AR6 scenarios. And if we consider only human-driven warming, then we exclude that. And we also exclude any sort of staying under or exceeding 1.5 just by solar variability by chance. So this is a complete human attribution of future warming. And then if we update this to 2024, then we lose all the scenarios that are 1.5 degree consistent, including those with the low overshoot. So this is really the sort of the takeaway message that measuring human contributions to global warming with the existing IPCC scenarios means that we can no longer remain with 1.5 degree consistency. So to summarize, 1.5 degrees without overshoot, whichever way you cut it, is no longer within reach, at least in the best estimates of the projections that we have. But every bit of climate action still matters. So we still need to, according to the Paris Agreement wording, pursue efforts to limit warming to 1.5 degrees. Because limiting the level of warming that we have is the only way to limit near-term and long-term climate impacts. So thank you.
Thank you also very much for our speakers. Wonderful presentations. Now I'm going to open the floor for our attendees, both on-site and online. So please feel free to take the mic if you have any questions.
So can you just explain that means officially now in the future sort of IPCC reports 1.5 is just not going to be achievable. This is effectively what the implication of this is.
So I can't speak for what a future IPCC report might say about 1.5 degrees. It's clearly, whichever way you look at it, I think my work here is only really sort of formalizing something that's probably quite obvious to most people. That by the time the next assessment report comes around, I think it would be quite difficult to say that 1.5 degrees is still possible. It depends on how things evolve in the next few years. Clearly, it doesn't look like we're going in the right direction in terms of the policy area. But yes, I can't preempt what IPCC might say, but that would be a rather large challenge for whoever is in charge of writing that section in the next report.
And then just about the harmonization, that looked like a bit of a fantasy. Suddenly emissions are going to drop. That doesn't look realistic at all.
So again, this is following what was the methods that was done in the last IPCC report. So again, if you sort of look at even the existing scenarios, look from a hindsight perspective, fairly far-fetched. They have a large reduction of emissions starting in 2020. And I think the point of this work is that hasn't happened. And I think it's not likely to happen starting in 2025 either. But it's kind of saying the further you move away from that purple plume, the harder and harder it gets to get anywhere near even 2 degrees as a sort of Paris Agreement consistent level.
Yeah, I have a question for Alice. So first, I may miss it, but how many participants did you have for your
It
study?
was roughly 1,000 per country, so 6,000 total.
Right. And next question is that as your study showed, there are quite big differences between the countries. And I can imagine that there are also quite big differences just even within one country. So at the moment I'm based in Belgium, and there, for instance, in Brussels, the implementation is different than in Leuven, and there it's different than in Hasselt. So even just within cities, the people's attitude towards applying, for example, some of these reduction measurements is very different. And so how would you implement these recommendations for policies on EU-wide level?
So I think it's correct what you're saying. We have seen in our data when we go in, we are starting then to see more groups unfold within that. And it's something that comes very naturally, I think, when we look at urban environments. I think our most important statement was to say that we can't have a blanket solution. The places are too different. And so that we might have to break away from that idea that we can make a single recommendation for the EU. And that is important.
Yeah.
Do we have any other questions on site or online? All right. Well, now we're going to conclude our second press conference and our first one of today. So I want to give a round of applause again for our speakers. You did a really great job, so thank you so much. So our next press conference is taking place this afternoon at 3 p.m. Berlin time, and it's going to be about NASA's Juno mission to Jupiter. So make sure to not miss it. And yeah, thank you again. Thank you for attending.